Hi, I'm Ryan Nickel, CTO at DSA Ocean, and today I want to talk about some reality checks you can do with hydrodynamic data you've processed using a ship motion prediction program like ProteusDS. So what we're really talking about here and why you'd be interested in this is that when you're working with ship motion prediction models and things are built up in layers of complexity, and you may go on to add even more complexity if you're doing a mooring analysis or some kind of more complicated scenario. It's really important to check things as you go along, and then you'll identify issues and errors ahead of looking at the end result of some very complicated setup and just really not knowing where to start and untangling all of that stuff. So right now we're going to focus on working with motion RAO data, and we're going to be focusing on ProteusDS, but still a lot of the lessons that we're talking about really apply to any program you'd be working with. So we're going to be looking at the ProteusDS ShipMo3D toolset first. I've got a trimaran project here I've been kind of playing around with, just not a real trimaran, but it doesn't really matter what kind of vessel you're using, whether it's monohull, multi-hull, a lot of the lessons still apply here. Now, for motion RAO data, remember that this is prescribing a motion for a floating system. It's been calculated somewhere else, and you're using this in another tool to drive the motion of a floating system given a wave input. So it's kinematic. We're not looking at forces. It just says, hey, you got a wave like this, then it's going to move like this. And there's advantages and disadvantages to that approach, but this is what we're going to focus on right now. So the main thing that you can look at to reality check this is that in really low frequency waves, or in other words, really long period waves, things will converge to following the sea surface elevation and following the slope of the wave. So heave motions follow the water elevation, pitch motions, roll motions follow the slope of the wave. And in fact, in the ShipMo3D toolset here, if you go to Seakeep Regular, this is the application that calculates the motion RAOs. And if we just look at this for the trimaran, at zero speed here we have, this is a following sea condition, which still applies, but we'll do head sea. Here you can see the heave RAO converging to 1 at low frequency, right? So it's following the water surface in heave. Now, and in pitch RAO, we see it also converging to 1. Now you got to be a little bit careful here because every seakeeping tool, ship motion prediction tool, is a little bit different. The ProteusDS ShipMo3D toolset non-dimensionalizes rotation by wave slope, in which case you will get the RAO for pitch and roll and stuff like that converging to 1, but not all programs are the same, so be careful about that. But yeah, so pitch, this is in head sea. It's going to approach the slope of the wave. And if we look at 90 degrees beam sea condition, yeah, we've got a peak here for the roll RAO, but then of course we need to get a bit more low frequency here, but you can see it's kind of converging to 1 here. And again, similarly with heave and beam sea, we see it converging to a value of 1. So those are that's a first check you can do with your seakeeping program. Take a look at the RAOs. But we want to be using this data in another tool, and we want to, how do we do that in, for example, the ProteusDS Simulation Toolbox. So in Seakeep Regular here, you'll see this little checkbox here, Export ProteusDS Response Amplitude Operators. So if you save and run that, and we'll look at the folder here, you'll see this file generated. So our project name here is trimaran, the file name prefix, and so you see this trimaran, and then ProteusDS oh no, that's not the right file. Here we go, trimaran ProteusDS RAO regular.dat. So I'm going to copy this file. What we're going to do then is load this in to drive rigid body motion in ProteusDS Simulation Toolbox, and we're going to do something similar with these low frequency waves. Just make sure it's following the surface and things are looking good. So first things first here, I'll just save this project. Okay, oh, we're already in the trimaran folder here, so we'll call this motion RAO trimaran. Okay. And now we need to copy the files in there. So here's a little pre-visualizer. I really like the water surface for reference there. Now we don't have, I'll make a rigid body here, trimaran motion RAO. Okay, so our folder is generated here. I'm going to copy and paste that RAO file here. For visualization purposes, I have a full mesh of the trimaran. I'm going to copy and paste that in here. I was working with this in Rhino earlier. This just gives it a physical representation in here. So in Simulation Toolbox, to drive a rigid body by motion RAO, we set kinematic to 3. And we'll right-click, resolve follower properties, and then it says, okay, well, which RAO feature do you want to use for this? Now, we don't have anything loaded up in here, so I'm going to, for my own organization, I'm going to call this trimaran 80 meters. So the vessel that we're working with here is 80 meters. It's arbitrary, 80 meters reference length there for what we're working with. I'll call that RAO, and we'll go to feature definition. And as a new project, we don't have anything in here. So this is where we now reference this file name here, like that. Okay, now let's add a visualization feature. So there's more than one way to do this. If you're sort of used to using it, you can start typing and away you go. Don't forget you got this right-click context menu here. Go to Insert Property, Visualization Model. We'll call this something easy to remember, trimaran 80 meter hull. And we'll go to feature definition, and I'm just loading the full hull file here. This is only for visualization purposes, and we're just going to flip that around. So this is 6 pieces of information: the linear, offset, and rotational offset. We got a roll 190 degree fixed roll difference there. Okay, so my best practice for working with ProteusDS ShipMo3D toolset and Simulation Toolbox is we just have everything set up with the rigid body reference frame at the aft baseline of the vessel. So you can see that there. That little soccer ball thing is the center of gravity. Well, let's just leave it there for now. If we go back here, note the draft baseline at midships is 3. So we'll set the rigid body state down to 3 meters there, and we got our sort of calm water displacement looking good. The motion RAOs will move relative to the initial rigid body position, so you want to make sure that that's kind of looking good. So we've got we don't have any waves turned on right now. Let's just see what happens when we run it. This is sort of like a calm water test, but it's not dynamically calculating the position of the rigid body, so it should just sit there. It's not a bad test to do before you get into the details of things. So we're loading post PDS up here. There's our trimaran. Double click on it and we can take a look at it. And I don't expect it to be doing anything. No bobbing, just sitting there. And sure enough, it's not moving around, not doing anything. Okay, not exactly the same as a calm water check, but it is not doing anything. So then we'll reset the simulation here, and then why don't we turn on some waves? Now, first, let's look at a really long wave period. So we'll set wave type 1. We'll just do a sinusoidal wave because that's pretty simple. And how long is a long period? Or in other words, low frequency, long period. Well, maybe for monohull type things, 20 to 30 seconds, right? Maybe we'll do 25 seconds. Now, the wave height kind of has to be high enough for you to see the slope and things like that, so we might do 15 meters. It doesn't have to be a realistic sort of wave condition for this. This is just checking what's happening. So again, the period is so long, the system is going to be following the wave surface, and the pitch and rotation is going to be following the wave surface. Oh, I made a little bit of a mistake. I really wanted to do head waves. Now, the way that this is oriented, it's pointing north with the x-axis here. So this wave heading also means it's going this way. It should be fine, but it's a following C. I just, for the purposes of, I kind of prefer doing head C conditions. So we'll do that. It goes really quickly. And now we don't have, what we can do is use this reload button here in post PDS. It attempts to reload the simulation. And I didn't turn on any wave ramping. That's sometimes a good idea to do, although it won't affect the results here. And so let's play back. So 15 meter waves, 25 seconds. That might seem kind of ridiculous. On the other hand, I have seen data that waves do get like this in the Southern Ocean, so it's not impossible to see things like that. Now, this is looking good. The period is so long, you can see how it's following the sea surface. And also the way in heave, it's following the water. We're not seeing drastic changes in the draft. There's no sort of inertia effects of the thing oscillating or anything like that. It's pitching up as it goes up the wave and pitching down as it goes down the wave, and we're seeing a nice even sort of displacement across here. So it's looking really good. That's the one check that you can do. Let's do a beam wave condition check as well. So we'll do 90 degrees here. Now this is absolute degrees in terms of the world reference frame, but again, just so happens that we have this set aligned north-south, so 90 degrees will give us a beam wave condition, and that's done really quickly. So we reload it here, and how are things looking in beam wave conditions? Now I'm going to grab the slider and just move it a little bit faster so we don't have to sit here and look at it, and things are looking good. Okay, not so bad. Now I do think it's a good idea to look at something more reasonable in terms of the an expected wave period and frequency. So maybe we'll do something like a coastal kind of wind-driven wave, 2 meter, 8 seconds kind of thing, and just see what happens. Now you won't have a number to compare with. Like you can't say, oh, if the RAO is going to be 1, which means it's following the sea surface. However, you can get a qualitative feel if something is looking wrong. So we'll look at this, and whoops! I made a mistake here. That's wave heading 8 degrees. That's not what I want. Now let's change the wave period to 8 seconds. I just got so excited. Okay, let's do a head sea again, and see what happens with that. All right. Okay, reload the data. So head sea condition, 2 meters, 8 seconds waves. Now, it won't follow the sea surface. There will be some bobbing relative to the water surface. So let's take a look at that. Now, something's wrong here, definitely. That is like so much green water on the deck. The bow is coming way out of the water. Hold on a second. That doesn't look right. That doesn't look right for this kind of condition. Let's take just a quick look back at our file setup here. Now, if we click on the line here for the RAO, there's some documentation here. Specifies the rigid body feature to load, and this drives the motions for the rigid body as a function of incident wave properties. For an RAO that generates the motion of the CG of a floating structure, the rigid body RAO feature should be placed at the CG location in terms of the rigid body local frame. Well, we haven't done any of that. So what we need to do is make sure we understand where the CG location is, and that's what the ShipMo3D toolset is doing. It's calculating the motions of the vessel where the CG location is, and that's what that RAO is describing. So we know that, for example, we set the CG above baseline. It's 5 meters above baseline. If we go and look at the motion RAO file, you'll see this reference position information here, and in fact that is the location that the RAO is describing. And it's where ShipMo3D has calculated the CG to be with our input of that 5 meters above baseline. So what we'll do is we'll put this in for the CG location. Now, if we look at the setup visualizer window here, you can see that little soccer ball shape thing. That's sort of much more in the middle of the vessel and 5 meters up from baseline. So that's looking much more realistic and good. So that's good. And then Proteus says, hey, if you want to use this RAO, if it's supposed to be calculating the motion of the CG, well, you better put in the same coordinates for that. So let's try the same exact run again. The only thing we've done is make sure that we've got our coordinate frames aligned here. We've properly specified the CG. I haven't changed the mass or the inertia because remember, this is a kinematic mode. It's not actually calculating forces. It's prescribing the motion of the system based on this RAO. So same condition, head sea, 2 meter, 8 second condition. Let's see what this is looking like. Now, it's not following the sea surface. We don't necessarily expect that, but certainly it's looking a lot more reasonable in terms of we're not getting any weirdness happening with the bow coming totally out of the water. It's getting a little tight here with immersion, but it is a very long and skinny vessel. We don't have a lot of bow flare and things like that. And this is kind of a steep wave condition all the same too. So this looks much more reasonable. We were taking a closer look at what it's asking to do, and this is making a lot more sense. And then finally, let's go back and look at a long period check again. So we'll go back to 15 and 25. We'll rerun this again. This is just to prove that nothing's changed in the low frequency high period case. So again, I'm just going to grab the slider and move it a little bit faster. On playback, we still see things following it. So we know that the motion RAOs converge to 1 for linear and rotational motions depending on the loading condition. For example, head waves, heave motion, and pitch motion follow the sea surface. Okay, that's looking good. For motion RAO stuff, it still pays to look at some kind of reasonable condition for wave period, just to look for something that looks weird. We shouldn't see the bow grossly coming in out of the water and stuff like that too. So a couple of reality checks working with motion RAO data. This is very focused on ProteusDS, but really a lot of the lessons here apply to any ship motion prediction tool you work with. And that's all for now. Thanks for watching.